Recording in progress.
All right, so we just said, unlike a straight line where the gradient is constant at every point on the line, it's not the same for a curve, right? My gradient here would be different from the gradient here. But how exactly would you find the gradient of a curve at a point? Well, that's where your knowledge of tangents come in. To find the gradient at a point on a curve, I would actually find the gradient of the tangent at that point. So if I wanted to find the gradient at this point, I would find the gradient of the tangent. Let's say the gradient of my tangent was 2. That's the gradient at this point. But if I drew a tangent to this point right here, and I found the gradient, well, remember tangent is supposed to touch only once, right? Let's just pretend this touches once. If I find the gradient of this tangent at this point right here, let's say it was 5. So the gradient at this point is 2, but the gradient at this point is 5. And we said the gradient is velocity, right? So we just for a second. That's why I said a curve shows that a body is moving with varying velocity. Varying meaning that the velocity is actually changing. Like this diagram here, 5 is different from 2, obviously, meaning that my velocity changed. And that's why we said, if there's a curve, that's varying velocity. So your velocity is changing. It's not the same. Because we know that the gradient of a curve at different points would not be the same. Do you understand that? Yes, no? Come on, I need.
Miss, could you go for it once again, please?
Okay. From which part? This whole point right here?
Yes,
The
miss.
varying. Okay. This is what you should be doing at this point since the exams are so close. Ask questions. Like, don't give me a break. Ask as many questions as you want. So this is X. This is Y. And let me just draw another graph down here with this straight line. X, Y. This one, straight line. And you know that the gradient of, well, let's pretend that's straight, right? And it's kind of cool, but it's supposed to be a straight line. You know that the gradient of a straight line is constant, right?
Yes, ma'am.
Right. But if I have a curve, actually, let me use a parabolic curve. Do you know that the gradients of a curve at each point, well, at different points, is not the same? Did you know that?
Yes, miss.
Okay. Well, oh my. We're not there yet. That's what we're moving on to next. So, parabolic curve. Do you know to find the gradient at each point? Well, at a point on a curve, we actually find the gradient of the tangent to that point. Did you know
Miss,
that? Unlike the straight line where we have a formula, the m is equal to, m is equal to y2 minus y1 over x2 minus x1. And then you take 2 points on the line, 2 random points on the line. So let's just say this point and this point. And you substitute them into your formula and you get the gradient, right? And the gradient is supposed to be the same for each point, for every point on the line. But because it's a curve, this is a curve and not a straight line, I cannot just apply this formula. I cannot take 2 points on this curve, let me say this point and this point, substitute it into my formula and say, okay, that's my gradient. No, because for a curve, at different points, the gradients are different. Do you understand that?
Yes, miss.
Right. So we needed a way to find out the gradients at the points. If I can't use this, then how am I supposed to find the gradient at this point or the gradient at this point? That's where tangents come in. To find the gradient of a point on a curve, we find the gradient of the tangent to that point. So remember, a tangent is a line that touches the curve only once. Let me just shorten this line. So if I want to find the gradient of this blue point here, this specific point on the curve, right here, I already established I cannot just use this formula because the gradient at different points would not be the same. So I use a tangent. Tangent, we know, only touches the curve once. Okay. If I want to find the gradient at this point, all I have to do is to find the gradient of this tangent. Do you understand that?
Yes, miss.
Okay, so that's how we find the gradient at a point on a curve, right? We draw a tangent and we find the gradient of the tangent to that point. But that's not what I really want you to pick up here. What I want
Miss,
you
the
to
tangent is like a 3/4 or half of a line, a full line.
yeah, it's actually a full line. So this wouldn't be right because it would actually pass and touch that. So the tangent would actually look like this. That's just my drawing, right? Let's just say you're familiar with circles. This is not what your graph would look like, right? Your graph would not look like a circle. But just to show you what I mean, I want to find the gradient here. At this point, I draw a tangent to the circle. Right. So this line extends, let's just say to infinity, and it only touches the circle at one point. It would extend all the way down here and it would never touch the circle again. Extend all the way up here, it would never touch the circle again. Only at this point. That's the definition of a tangent. Do you understand that?
Yes, miss, got it.
Okay. But that tangent thing, that was just like a little fact. You're actually supposed to know that, eh? Supposed to know that. Well, that's not really what I wanted you to pick up on. What I want you to know is that because the gradients at the points are different. Unlike a straight line, where the gradient of this line would be constant, it doesn't matter which points I choose, the gradient would always be the same. It's not the same for a curve. The gradients are different. And because the gradients are different, and the gradient of this graph is velocity, that means that my velocities would be different. And that's why I said varying velocities, meaning that it's not the same. The velocities are changing. Do you understand that?
Yes, miss.
Okay. So why did I say i.e. it's accelerating or decelerating? Well, this is why it's important for you to know all those formulae and the definitions. I know it's kind of tedious, but you have to. That's the only way you would fully understand this topic, right? So, I mean, you could just memorize, but you see, when it comes to pulling information from a graph, sometimes it might give you trouble if you don't fully understand what the terms mean and you just memorize it. It can actually give you trouble when it's time for you to pull information from a graph to use it, right? So just keep that in mind. You need to understand. It's not about memorizing, it's about understanding what's going on. So why did I say there's a acceleration or deceleration. Well, acceleration, we said the definition is the rate of change of velocity. That's my final velocity minus the initial velocity divided by the time taken. If I have a change in velocity, well, if my velocity is changing, right? So I have a change in velocity, varying velocity, I have a change in velocity. That means that I have an acceleration, because this is the change in velocity. You might see delta V, something like that. And because I have a change in velocity, and of course I have my time, then I have an acceleration. You would actually see, we would do a question like that just now. So just in case you don't fully understand what I just said, you do a question like that just now, right? Just keep in mind, varying velocity means I have a change in velocity. And if I have a change in velocity, because of my definition of acceleration, I would have an acceleration or deceleration, depending on the sign, right? Positive means acceleration. If I have a negative, then it's deceleration. Horizontal line means that the object is stationary or at rest. So let me just draw a graph again. Displacement is y, time is x. If I have a horizontal line going like this, at this point, hold on. Right, so let's say this is my graph, and that's my horizontal line. Let's just say this is 4 meters. At this point, it's 1 second. So remember, this axis represents time, right? At this point, it's 2 seconds. At this point, it's 3 seconds. So time is going by. The time is going by. It moves from 0 seconds to 1, then 2, then 3. But notice here, the body is not moving because it's still at 4 meters. I'm trying to wait. Let's say this is trying to make this as simple as possible. So let's say this is 0. This is 4. My body is here. It starts off here. So from my starting point, which is 0 meters, I'm actually at the 4 meter mark, right? But I realize time is going by, but I'm still at this mark right here. So if time is going by, I'm counting 1, 2, 3, and I realize that the body is just staying at this 4 meter mark. It's not moving to the right, it's not moving to the left, it's not going anywhere. It's still at this 4 meter mark, even though time is going by. That means that the body or the object is stationary or at rest. It's not moving. It's just staying at that 4 meter mark. Do you understand that?
Yes, miss.
Yes, miss.
Okay, nice. Let's do a question now. Okay. So, an athlete is training by jogging in a straight line. Displacement time graph below shows the displacement of the athlete from a starting point through a motion. Starting point, motion, right? Displacement time graph. Displacement is on the y, time is on the x. Calculate the velocity of the athlete during the first 2 seconds. First 2 seconds, I know time is on my x-axis. So first 2 seconds, I see 2 seconds here. Velocity. This is a question, right? How is velocity related to this distance time graph? Displacement time graph, sorry. How is velocity related to it? Crickets. Displacement time. Yeah, but what is velocity? If I have a displacement time graph, how would I find the velocity? How would I use this graph to find the velocity? The graph gives velocity. But how would I use this graph here to find the velocity? Can I just read it off, or do I need to calculate something? Calculate. Calculate what though? What am I calculating to find the velocity? Gradient, yes. So velocity is the gradient of a displacement time graph. So if they want the velocity of the athlete during the first 2 seconds, so that's this from 0 to 2, I need to find the velocity, the gradient of this line. The gradient of this line would give me the velocity. Do you understand that? Do you understand how I would find the velocity during the first 2 seconds? So from 0 seconds to 2 seconds.
Yes, miss.
Okay, so can you do that for me and tell me what answer you get? Find the gradient of this line. Anybody has an answer? Okay, just in the interest of time, I'll go through this, right? Velocity. Velocity is a gradient. That's what we're trying to find, right? Because they want the velocity, I need to find the gradient of this line. Notice it's a straight line, right? So it doesn't matter which 2 points I choose, the gradient would always be the same because gradient of a straight line is constant. But there are really only 2 points that I can use on this line. This point and the origin. Why can't I use like a point here? Because I don't know what value this is. This isn't like they gave me a scale and I could actually work out what this value might be. No. There are only 2 clear points that I can use. This point on top, and they told me it's 2 and 5, and then this point right here, which I know is the origin, so it's 0, 0. So therefore, the points that I would be using to substitute into this formula, this would be y2, this would be y1, and then my origin would be, let me y1 now. This would be x2. And then my origin, which is 0, 0, would be y1 and x1. So I'm trying to find the gradient. Gradient is velocity. So let me just write a v. y2 is 5. And then because this is the origin, the y1 value would be 0. Just in case anybody forgot, the coordinates of origin is 0, 0. So my y value, so my x value is 0 and my y value is also 0. So that's why I have 0 here, right? 5 minus 0, x2 is 2. And for the origin, the x value is 0. This is meters, this is seconds. 5 minus 0 is 5. And then 2 minus 0 is 2. So the velocity during the first 2 seconds is 5.2 meters per second. Remember, you could write it like this, or some people write the unit like this with a slash. Yeah, so you could use 2.5 meters per second. Yeah, you don't have to leave it like this because it's an exact decimal. So yeah, let me just put all 2.5. Well, yeah, that's an S. It looks like a 5, but anyways, that's the answer. Anybody did not get that, or you don't understand? Even if you didn't get it, do you understand why that is the answer now? Yep. Cool. So describe, I'll leave this to the side for whoever's taking it down. Describe the motion of the athlete between the times of 2 seconds, 2, and 5 seconds, 5. I have a horizontal line. So if I have a horizontal line, can anybody tell me what does that mean? She remained at rest. Yes, good job. So just going back here, horizontal line means the object, in this case is a person, is stationary or at rest. Right. Calculate the velocity. Again, velocity. We know whenever we see velocity for displacement time graph, that's the velocity is the gradient, right? So we know we calculate in gradient. Calculate the velocity of the athlete at 10 seconds. So 10 seconds is somewhere around here. Okay, we know we need to find the gradients, right? We need to find gradients. But somebody, you might get confused as to how exactly am I supposed to find the velocity at 10 seconds if they did not give me the time at 10 seconds? Like they didn't give me the displacement at 10 seconds. They didn't label 10 seconds anyway. So how am I supposed to find the velocity at 10 seconds if they didn't give me any values for 10 seconds? That question might be running through your mind. But you need to remember, this is a straight line. Yeah, it's moving downwards. So it's a downward slope. But it's still a straight line. Straight lines always have constant velocity. So it does not matter if I take a point here, a point here, a point here, a point here, anywhere on this line. Once it's on the line, this velocity is going to be the same. So for this particular question, you might get confused, like I said, because they did not label the 10-second mark and it didn't give you any y value for this 10 seconds. But that doesn't matter because the gradient of a straight line is constant. So I can actually use these 2 points that they actually gave me to find the gradient of this line. Whatever gradient I get, it would actually be the gradient at 10 seconds. Why? Because the gradient of a straight line is constant. Do you understand that? Yes, no?
Yes, Miss.
Because I know that may have confused somebody. And it's okay, because now you know. So, because we're almost out of time, I'll just do it now, right? This value is my x1. The y1 would actually be 0 because it's touching the x-axis, right? So my displacement is 0. And then at this point, it's 8. So x2 is 8. y2 is 11. y2. So just substituting those values, y2, 11, y1, 0, x2 is 8, y2, wait, y1 is 14. Why do I have that line there? Hold on, let me just erase that blue line. All right. 11 minus 0, that's 11. But there's a problem here. Well, it's not really a problem, just it's different from what we just did, right? Because 8 is less than 14, and 8 minus 14 is minus 6. So that's a negative number, right? But like I said, don't panic. Do not panic. Why? Because like we discussed before, if I get a negative value, that doesn't mean anything is wrong, right? It does not mean that you did something wrong and you need to check over. Why? Because velocity is a vector quantity, meaning that I can actually have a magnitude and a direction. So you see that negative sign? All that tells me is that I'm moving in the opposite direction. That's it. That is basically it. So in terms of this athlete and her moving and all of that, let me just, like I said, a diagram always helps, right? So what color, what color? Yellow. Let's say this is the track. And she starts at 0. Yeah, just my stick man. Yeah, anyways. So she starts at 0 and she's moving, she's moving, she's moving this way. She's moving, she's moving. And around here, she stops. She stops to take a little break. You know, she's tired. Then she continues, move. So this is, oh my, where's my name? Let me use a red. Yeah, you can see this. So she's moving, she's moving, she's moving. Then she rests. So she's here. She takes a little break for 3 seconds, from 2 seconds to 5 seconds, right? So for 3 seconds, she takes a break. Then she continues moving, she's moving, she's moving. And then she comes here. But then what happens at this point? She actually goes this way. She goes back this way, all the way down. She does not take any breaks. After taking this break right here, she runs all the way to her final destination, which is, let's just say, okay, it's an athlete. So what did she do? Run to the finish line? Or did she run back? Anyways, let's just say this is the finish line. Whatever, a banner, whatever, yeah. So that's the finish line. So she runs, she takes a 3-second break, then she continues running until she reaches the finish line. But then let's just say she needs to, I don't know, run again. So she goes back to the starting position. From the finish line, she runs all the way back to the starting position. But this time she does not stop, she doesn't take any breaks. She runs all the way back. Do you understand this diagram? I know it's not the best, but do you understand what this graph is telling you? Like based on my diagram with stick figures. True and actress.
Wait, this one is
those people.
the velocity, right?
Huh?
Wait, which one are you doing now? The letter B or C?
See,
Oh, okay.
1.83 meters per second. I just drew like some stick figures to show you what's actually going on. What does this graph tell me? She's running for 2 seconds. She takes a small break for 3 seconds. Then she continues running all the way to the finish line. And then let's say she needs to run that distance again. So from the finish line, she goes all the way back without any breaks, back to the starting position. That's what this graph is showing you. That's what I wanted to make clear. So that negative sign does not mean you did it wrong, because velocity has both magnitude and direction. What this negative sign tells me is that instead of running, let's say to the right, when she reaches here, she starts running to the left, back towards her starting position. Do you understand that? Yes, no? Did I confuse you? Please let me know. I need to know. No comment, okay. Well, I'm moving on. Find the total distance traveled by the athlete during the 14 seconds. So how would you do that? Any ideas? Not sure. Okay. We don't understand the topic. Okay. That's a problem, huh? Because the reason I am doing this is to help you to understand. So the fact that you still don't understand, but you're not asking me any questions, that's a problem. Find the total distance traveled by the athlete during 14 seconds. So how would I go about finding the distance? Well, I can actually read it off my graph, because I know she went here, went up, side, down, right. So from this point to this point, that's actually 11 meters. So she ran for 11 meters from this to this. That's 11 meters. And then she actually ran the 11 meters again, because she went from here back down to her starting position. So that's 11. And let me just draw a straight line down here. 11. 11 and 11 is 22. So her total distance travel is actually 22 meters. Do you understand that? Okay. Distance time. Let me just do the distance time and then we'll end there because it's kind of similar. Key features. Distance is on the y. So instead of displacement being on the y-axis, now it's distance on the y-axis. Time is on the x, right? Because it's a distance time. The gradient in this case is speed, not velocity, but speed, right? Slight change, nothing major. Just instead of velocity, it's speed. Why? Let's go back to our definition. Distance per unit time. So speed, let's just say it's denoted by S, is my distance on time. Distance on time is speed. That's why my gradient in this case, it's not velocity, which is displacement on time. It's speed, which is distance on time. Although, to be fair, I've seen people using speed and velocity interchangeably when it comes to graphs, right? So you might see someone talking about how the distance time graph, the gradient is velocity. I mean, technically it's not, right? So yeah, there's a, like I said, it's a slight change, right? It's a difference. Gradient is speed. That's what you need to know. The gradient is speed. But like I said, to be fair, some people say it's velocity, but that's really not true because distance on time is speed. It's displacement on time that's velocity, right? Straight line shows that the object is moving with a constant speed. Same thing. Here, you said constant velocity, but now since the gradient is speed, you would say it's moving at a constant speed. That's why I said the difference isn't really major. The curve show that it's moving with a varying speed. Before it was varying velocity, now it's varying speed. Horizontal line means that it's at rest. Makes sense because it's not moving. Note, this is really the major difference between the distance time and displacement time graph. This distance time graphs cannot go below the x-axis, but displacement time graphs can. And you might be wondering, but why? So just let me tell you this. You see, for all of these graphs that you're required to know, you would never, So this is time. This is distance in this case. It's distance we're dealing with, right? So let me just tell you now, for all of these graphs, you would never, ever, ever, ever cross this vertical axis or the x-axis and get a value somewhere here. Why? Because it's time. You cannot have a negative time. Time is a scalar quantity. And that just does not make sense. You can't have negative time. So you would never cross this y-axis. But it is possible to cross the x-axis, the displacement. So for distance, not displacement, for distance, my graph